Scan the standard periodic table, and you will eventually find a disconnected row of 15 elements sitting by themselves at the very bottom. For most people, they are a footnote, an exiled group of outcasts that seem separate from the rest of chemistry. But those 15 elements provide the specific physical properties required to run our smartphones, amplify the global internet, and drive the massive motors of every single electric vehicle on the road today. These are the lanthanides. They share a nearly identical valence electron configuration because of how they fill their internal f orbital. Because this outer shell of electrons looks the same across the entire row, these elements exhibit nearly identical chemical behavior. This chemical similarity makes them incredibly difficult to isolate. In nature, they act like twins, bonding to the same minerals and resisting efforts to separate one from another. However, while they react chemically in the same way, the subtle atomic differences in their inner shells give each element a specialized physical superpower. One group of lanthanides possesses unique electron spins that allow for the creation of incredibly strong permanent magnets. Neodymium, element 60, is the primary driver of this technology. Its magnetic strength is what allows the massive motors inside wind turbines to convert wind into a steady stream of electricity. Because pure neodymium magnets can fail in high-temperature environments, engineers add praseodymium and dysprosium. These elements reinforce the magnetic field, allowing it to remain stable even inside the heat of an aircraft engine. Farther out, samarium is used to power precision instruments across the solar system, providing reliable magnetic force in extreme environments where traditional materials would lose their effectiveness. These magnets act as the muscle of modern technology, converting raw motion into power and driving the global transition toward electric transport. Other lanthanides interact specifically with photons, changing how we transmit and view information. Lanthanum, element 57, is used to sharpen the glass in modern camera lenses, allowing for greater clarity in high-end optics. The brilliant red hues on our modern screens and smart displays are produced by europium and terbium. Without them, digital displays would lack the color depth we have come to expect from modern technology. Underneath the ocean, erbium functions as a signal booster. It sits inside fiber optic cables, quietly amplifying the light signals that carry internet data across the seabed and into space. These light-manipulating elements are the reason our digital world remains visible and our global communications stay connected. In medicine, gadolinium acts as a contrast agent. It makes specific tissues visible during an MRI, allowing doctors to see the internal structures of the human body with high clarity. Thulium and lutetium extend these medical capabilities by enabling the production of compact X-ray devices and highly sensitive tools for detecting disease. For deep space exploration, promethium provides a steady source of power. This rare radioactive metal generates energy for instruments in regions where sunlight is too faint for solar panels to function. Holmium provides the pinpoint precision required for surgical lasers, allowing for delicate medical procedures. Cerium is used to create sparks and functions as a catalyst inside catalytic converters to actively clean vehicle emissions before they leave the exhaust. Ytterbium is utilized in the construction of atomic clocks. It provides the timing precision required for global navigation systems and the development of quantum technology. These elements allow us to operate across a vast scale, from the microscopic details of a human cell to the navigation of deep space. While they are known as rare earths, these 15 elements are actually found in significant quantities throughout the Earth's crust. The difficulty lies in their separation. Because they are chemically identical, they bond tightly to other minerals, making it an industrial challenge to pull them apart into pure forms. The rare part of the name refers to the difficulty of finding them in concentrated deposits, making the effort to refine them a massive industrial and geopolitical undertaking. The next time you look at a periodic table, remember that the disconnected block at the bottom is not a group of outliers. These elements are the silent engine of the modern world, providing the foundation for clean energy, advancing space travel, and next-generation scientific precision.